Go. Welcome everybody for our DMG seminar of our weekly meeting in the Department of Marine Geosciences. And today we are very honored to host soon to be Dr. Nir Badt, right?
I'm already a doctor.
Sorry. So Dr. Nir
It's
Zeev
okay.
Badt,
It's just a title.
that is at the Hebrew University in Jerusalem and the GFZ Center in Potsdam. And now you present yourself. Thank you, Neil, for coming.
Yes. Okay. So thank you for coming, everyone. And my name is Nir. I did my BSc and MSc in geological sciences in Ben-Gurion University. And then afterwards, I moved to do my PhD work at Brown University in the US, where I worked on friction problems during earthquakes. And afterwards, I moved to do a postdoc in the University of Pennsylvania. And I stayed there for like 2.5 years, almost three. And after that, I went back to Israel, where I hold a postdoc position at the University of the Hebrew University. And again, I work on earthquake-related problems, and I also have a part-time position here at a German institute, GFZ in Potsdam. And so my research focus is on rock mechanics related to geophysical problems, specifically earthquakes, but not just earthquakes. And today I'm going to talk about how small phenomena like molecular interactions and bonds have a control large phenomena like faults and how they heal over time. And so I hope I can convince you of the relationship between these two. And so. Yes. So I'll skip this because we're a bit short on time. I'll skip the first introduction slide. I'll just say that I combine methods and techniques from geology and rock mechanics and material science to study and tackle earthquake-related problems, earthquake physics-related problems in geophysics and in geology. And the focus for today's talk is the subject of fault healing. So we can look at the seismic cycle use in a generalized way, and if we look at this plot from Di Toro et al. From 2012, we can say in general that faults behave through these three processes, where we have on the y-axis, we have the fault strength in the dashed red. That's basically the resistance of the fault, the frictional resistance of the fault to slip along the fault surfaces. And the gray solid line is the shear stress. That's actually the traction or the stresses that are working, trying to push the fault towards sliding. And in green, we have the slip itself. That's displacement along the fault. So what happens in between earthquakes or before an earthquake? The shear stress increases. It doesn't have to follow this linear trend over time. Of course, x-axis is time, so shear stress increases just from tectonic loading. And at some point, the stresses on the fault reach the strength of the fault, where you see those two curves meet. And at that point, we are going to nucleate an earthquake. And during the rapid slip, we'll have a very short amount of time, we'll have quite a bit of slip accumulated on the fault. The stresses on the fault are going to relax due to the consumption of energy, of the elastic energy stored before. And the fault strength is also going to decrease through different physical processes like thermal weakening, increase in pore pressure, and other physical processes themselves. But after the earthquake has consumed all the energy and the fault basically stopped rupturing and slipping, then we have an interseismic period where we see a post-seismic healing. So the fault strength increases again over time at some function or another. And of course, also the shear stress also increases over that time period as well. So because because we're resuming tectonic loading, and that happens until we reach the strength of the next earthquake, and so forth and so forth. So we have this cycle where we have an earthquake and healing, an earthquake and healing. So while earthquakes are interesting and very dramatic, we're going to focus on the time between earthquakes, so the post-seismic healing. And the reason is that healing is very, very important process. That's healing of the faults and the surfaces themselves. And that controls the spatial extent of the earthquake, the amount of stress drop. So think about it as more healing, we can accumulate more higher stress. So during an earthquakes, we start with a higher stress level, then we can drop these stresses. Higher stress level, higher stress drop, and stress drop corresponds to the earthquake magnitude in our understanding. And also the recurrence interval between the earthquakes, so greater amount of healing, a longer recurrence interval between earthquakes. And also experimental studies have shown that healing also controls the radiated seismic waves from the fault, and also the rupture style and the dynamics themselves. So there's a multitude of phenomena that are interesting and are related to the fault healing, which at this point we need to ask ourselves what exactly is fault healing. So we can categorize fault healing into two groups or two families of processes. The first one we'll call frictional aging or aging of rock contacts. That's basically if we think of the fault being made up of contacts between different rock surfaces and the grains that are contacting each other, if we're thinking about gouges and materials like that, then this frictional aging is the increase of friction along the contacts themselves, at the surfaces themselves, between the grains or between the surfaces themselves. So that's an increase in friction over time. That's aging. The second group of processes is cementation or cementation processes. We think about all the cracks within the rocks or the spaces between the grains themselves, the pore space, where that's can be filled with air or water or some kind of solutions. Then over time, we can precipitate secondary minerals between earthquakes, and these minerals seal up the fault and can really strengthen the rock itself or the rock mass itself and change its rheological response. So these two processes work in tandem, but over very different timescales, and they are both considered time dependent. And we're going to focus on the aging processes itself. There's two reasons for that. First of all, is that aging, because we increase the friction itself, the friction coefficient of the surfaces, if you will. That means that as we think about going deeper and deeper into the earth, we have an increase in normal stress on surfaces. That means that the contribution of friction is going to be much more significant than cementation of the rock mass itself. And in addition, so that's we're going to have a stress-dependent effect of the aging. And also, the cementation process is not well documented in experimental studies because it takes a very, very long time. When we're talking about geological timescales to actually precipitate these secondary minerals to seal up a fault. So we are going to focus on the aging process in this talk. If you look at this diagram over here, this is a fault from the Apennine faults, from the Apennines mountains in central Italy. The faults themselves, like many other faults, going to display a very complex mechanical and rheological architecture. We have cataclasite and ultracataclasite, which is a very highly deformed rock, competent rock, veins. So these are very complex features, but we have these processes that work together where we have the aging, which occurs at the surfaces of the grains within these units, or in the cracks, and the cementation itself. Okay. So the first thing we're going to talk about is going from the field to the lab, because earthquakes occur obviously at the field, but we need to try to simulate these types of behaviors at the lab scale. And if we look at the diagram over on the right side, that's this anonymous block sliding across a anonymous surface over here. We pull on it on the block itself, or we can push it, doesn't really matter. And when we try to mimic or simulate these interseismic behavior or interseismic healing and aging, people typically do these slide hold slide tests. We're sliding the top block at a constant velocity. We reach steady state friction. That's friction in the y-axis and time in the x-axis. So friction is at steady state, and at some point we decide to stop pulling. So we go into a relaxation of the stresses, and so friction relaxes as well as we go into the hold period. And at some point we decide to reslide again, and that's when we see this peak is increase in friction altogether, and the peak. That is basically, we can say it's the static friction coefficient, as we know from introduction to mechanics, which evolves into a steady state friction as before. The change between the steady state and that peak, that is what we call the frictional aging, or the change in friction, or the increase in friction, which is dependent on the hold period itself. So friction is a bit of a strange concept, but when we think about it, it's kind of straightforward, but it's also a bit more complex than what we typically think of it. When we have two bodies in contact, two solids, and that's true for any type of material, whether we're talking about rocks, metals, or any other types of synthetic or natural materials, at some scale, which typically is the small scales, at micro scale, even a seemingly flat surface is basically made of these rough contacts at small scales, meaning that these two bodies actually touch each other through these topography maximas, these bumps. We call these bumps asperities. And so when two bumps touch together, we call this like an asperity contact or asperity junction. But what we see right away is that the real area of contact is much smaller than the nominal one, than the flat one. And this is not anything new. Leonardo da Vinci wrote about this in his diaries about 500 years ago. And so this is well known in mechanics and has been discussed thoroughly. But what we can say is that the friction force is basically the inherent shear strength, that's tau sub c, shear strength of each asperity contact times the contact area itself. So that's talking about the real area of contact. So the global friction force for this two-body system would be just a summation across all the contacting asperities over here. So we have two factors that we need to consider: the contact strength and the contact area. So people have done these types of experiments, slides, many times and on different materials, and there's a lot of robust literature and experimental literature related to that. And what they found is that in general, delta mu, or the frictional aging, increases linearly with the logarithm of hold time. This is a figure from I think Beeler et al. And from 2022. And the thing is this experimental observation is very powerful, and it works for a whole uh, bunch of materials, whether we're talking about rocks, crystalline, sedimentary, or we're talking about gouges and any type of loose material or granular materials, glass and wood, and even polymers and other synthetic materials. This just holds up very truly for very different materials, which kind of implies that there is some underlying physical mechanism that is related to all these materials, that is relevant to all these materials. So just remember, take away that the frictional aging grows linearly with the logarithm of time. So in terms of rocks, there's a classic paper from Dietrich and Kilgore from '94, and they determined that the mechanism that controls the increase in frictional aging is due to plastic deformation. And what do they mean? Going back to our microscopic topography and the asperity contacts, if we let's just idealize one of these contacts as a sphere on a rigid surface, then they showed for different types of materials that as time increases logarithmically, the sphere undergoes plastic deformation. So we're going from a real area of contact, which is just the tangent between the flat and the sphere. The sphere is basically getting deformed plastically, so it changes its shape, and the contact area actually increases, and that occurs over the logarithm of time. So a linear increase in contact area over log time corresponds to a linear increase in friction with the logarithm of time. So they kind of solve the mystery of how friction evolves. It just increases because of contact area growth. And that, for many years, has been the underlying physical explanation to how friction evolves in between earthquakes, basically. And that interpretation goes into the widely used friction models that are used to interpret experimental friction studies. And they are also used in almost all earthquake rupture and landslides models. And when we have when we introduce these types of models into the friction model into these earthquake ruptures and landslide models, we affect and influence the predictions that we make from these types of models. So any geohazard estimation, basically. But there are a few things that are problematic with that. First of all, these interpretations of the contact area growth as the control mechanism on friction, it really has been done at room temperature and at conditions which might be humid or dry, but there's like no chemical complexity to it. And when we think about faults and geology, then it's all complexity, right? Because faults occur at very deep portions of the crust, kilometer depth, high temperatures, with fluids that can be brines or either hyper saturated fluids. And in addition, that friction model that friction model that relates contact area to the increase in contact area still does not explain the full range of frictional behaviors that we see in lab conditions. So there's some limitations, and so we're introducing these uncertainties into the models themselves. This is where we start talking about the contact strength. So if you remember, going back to that equation, simple equation for friction as the summation of the contact strength, tau sub c, times the contact area, we've just been talking about A sub c, the contact area. But the contact strength, what is the contact strength, basically? What are we talking about? So in a silicate Earth, which is our Earth, and the most abundant elements within the crust and mantle is silicon and oxygen. Let's focus on silicon oxide, okay? Silicon with two oxygens. We know that is quartz in its crystalline form, or silica, or just glass in its amorphous form. And it's also the basis for all the silicate minerals that are formed in that make up the mantle and the crust, except of course sedimentary rocks like limestones and dolomites. So there's a good reason why we are interested in this type of chemical system, the silicon with two oxygen. So studies in the last 10, 15 years, mostly coming from material science, have pointed out and shown that across the two bodies that are made up of silicon oxide, when we look at these asperities, the small scale asperities, silicon will form chemical bonds with oxygen and bridge to the next silicon from the other body, and form these silicon-oxygen-silicon chemical bridges that we call them cytoxane bonds. And that will, so basically we're forming chemical bonds across the interface of these two silicon-rich bodies. And when they did these slide-hold-slide tests with atomic force microscopy methods, they shown that the frictional aging stems from chemical bonding and not from what we typically say from the contact area itself. So it's a bit more nuanced, but it's a really important mechanism. It's a really important observation that aging, the frictional aging, corresponds to the chemical bonds that form across the interface itself, at least when we're talking about silicates. So these observations are very unique and very powerful, but they also have some limitations to them. The thing is, it's these scales that come from the atomic force microscopy are really, really small scales. These are nanoscale friction tests. And to scale nanometers into faults that can be tens, hundreds, or maybe even 1,000-kilometer long features, it's really, really challenging, and there's basically a leap of faith. So most geologists wouldn't be bothered from these experiments, from these nanoscale friction experiments, and there's a good reason for that. I mean, that's a really big scale, jumping scales. Also, the nanometer scale context from the AFM, it's where the intermolecular forces live. So it doesn't necessarily mean that it has an effect on the bulk mechanical frictional behavior of these contacts. And in addition, that the stresses associated with these experiments are very, very low. So we can't really trigger any plasticity. So contact area growth is just eliminated altogether in these types of experiments. And lastly, I would say that these, because of their small scale, and we're talking about chemistry is difficult, any contamination is going to have an outsized effect on the frictional behavior. So there's high sensitivity to the chemical environment that we're thinking about, that we're dealing with. If the experimentalist from these type of experiments was not careful and touched the surface with their bare fingers and contaminated them with a little bit of grease, like hydrocarbons, or the humidity level in the lab was slightly higher, then that would have go into the resolved friction on the resolved friction at these scales. It's really, really sensitive to all these types of changes. So again, when we're thinking about faults, maybe it is irrelevant to fault behavior. So I intend with my work to bridge this gap, and I do this with nanoindentation. And nanoindentation is a technique used for many, many years in material science, but not so in earth sciences. The idea is that we can indent a tip, typically made of diamond, into a sample using a normal force head. So we just indent it into the sample. And with a new kind of nano indenter, we can also translate the tip across the sample. Basically, just do another friction test or scratch test. Um, the nice thing about the nano indenter is that, first of all, we can do various types of tests, but we have control over the tip geometry. We can use spheres or a three-sided pyramid as shown in this close-up. Or we can use a flat punch. And we also control the tip substrate mineralogy and the environmental conditions with high accuracy. In addition, we have a very high precision with a nano indenter. That means that it's called a nano indenter because we can control the instrument at the nanometer scale, meaning we can translate the tip at nanometers per second rate or displacements of nanometers, but we have actually a quite large contact, where at least compared to atomic force microscopy, of about a few microns. So why does that matter for faults? Well, it matters a lot, and it's really nice because the contact area from nanoindentation is comparable to the small scale roughness in natural faults and in experimental faults. If you look at this diagram of power spectral density, which you can basically translate it as the roughness of a fault compared to the wavelength or the length scale that we consider. The natural faults display a linear relationship. It's basically a power law between the power spectral density and the wavelength. And for the small length scales or the little or the small bumps on natural faults, you can see that the nano indenter contact size is actually contact area corresponds very nicely to the length scale of the small bumps in natural faults. In dashed lines, I also include the PSD profiles from experimental faults. AFM, or atomic force microscope contacts, sit a bit lower than that, and mind you, this is a logarithm scale. So we have a sweet spot where we can tap in and understand the mechanics of the small scale roughness of natural faults. In addition, we can apply quite a bit of pressure, kind of quite a bit of contact pressure on these little bumps that we are testing with the nano indenter. And we can reach a contact pressure of about 11, 13, 14 gigapascals. Just so for reference, 11 gigapascals corresponds to about a normal stress on a surface at the depth of 400 kilometers in the Earth. So way beneath the seismogenic zone. That ends about 12 kilometers, and about halfway deep into the most deepest earthquakes ever recorded. That's if you're thinking about subduction zone earthquakes, but really, really deep earthquakes. And the most powerful thing about this method is that the contact area itself can be continuously monitored through continuous stiffness method, which is the bread and butter of nanoindentation. And that means we have the contact pressures, we got the small scale roughness, and we can monitor the contact area itself during an experiment. So let's look at very simple slide hold slide test only with a nano indenter. We're scratching the surface. I'm using a three-sided pyramid, this pointy tip, sliding directions from right to left. You can see here the scale of this picture, 10 microns. We're sliding 10 microns basically. This is diamond on quartz, natural quartz. Uh, Time on x-axis, friction on the y-axis. I start sliding, I reach the static coefficient of friction, then start slide in steady state friction. And at some point, I invoke a hold. I stop pushing on the tip. I go into a relaxation of the shear stress of the shear stress or the friction during the hold. And I start sliding again. At the end of a 10-second hold, you can see the peak and the delta mu. We can basically do the same slide hold slide test with the nano indenter. Oh, sorry. Okay, so what happens? During the test, we can monitor during the hold. I can monitor the contact area, and you can look at the right frame at B, and you can see that the contact area it's normalized by the initial contact area at the beginning of the hold, and you can see that contact area grows with the logarithm of time in a linear fashion. Here's the slope. Contact area grows linearly for different hold durations, 1 second, 10 seconds, up to 1,000 second holds. So we got that part. Contact area increases. However, when I plot everything together, so this is frictional aging at the y-axis versus the logarithm of hold time and the x-axis, I find that even though contact area increases, the frictional aging actually stays more or less constant, maybe drops a little bit. There's no correspondence between frictional aging and contact area growth, which is considerable because it contradicts the whole part of the introduction that I just gave you. So we're missing a key physical mechanism. And remember, we're talking about diamond quartz contacts. And that means diamond on quartz, it's basically a chemically inert contact because diamonds are kind of snobs. So just to do this halfway summing up, we have a geometrical increase in contact area, but we don't have a corresponding increase in friction because we're missing a key mechanism. And what I'm trying to convince you is that the key frictional mechanism is the formation of silicon-oxygen bonds. That's siloxane. So we need to do a new set of experiments to see if we can address this. And I address this using adhesion testing or pull-offs. So a different nano indenter, basically same instrument, only just a uniaxial one. And the idea is just indenting the tip into the sample, into a substrate. This is a diagram of a spherical tip into a substrate. I load it up, and then I unload it. And when I get to the point where load is basically zero, I see that I need to apply a little bit more load just to detach the tip from the sample itself. It kind of adheres together, kind of sticks to it. This adhesion force is basically a function of the contact area, which we know, and the strength or the bonding between the two materials. This is, of course, number two is of course an exaggeration of how it actually looks. But that's the main idea. Just do adhesion testing, and we do this in a very simple stress field. We're just doing uniaxial loading and unloading. So there's no shear stress that complicates the whole thing. I test different nano indenter tips, either made of diamond, which is chemically inert, versus quartz, which is chemically active, right? We can machine the quartz to fit into these holders. Well, we don't do that, but our friends in Switzerland do that for us. And the geometry itself, you can control. You can look at different geometries of a tip, of a sphere or a three-sided pyramid. And that's important because the sphere would be just an elastic contact, whereas the pyramid will be a plastic contact. So we have different stress field underneath the tip. In addition, the substrates are all going to be chemically equal, but mechanically different. They're all going to be silicon oxide. We're going to test natural quartz single crystals, synthetic quartz single crystals, and synthetic fused silica, which is basically glass, and that's amorphous. So the tests themselves look like very simple tests where we increase load. Look at the red curve over here. We increase load. That's load on the y-axis, the applied force. And then we unload it. You see we reach maximum load here in this test of about contact pressures of 13.8 gigapascals. This is diamond on quartz. And then we unload it here and go back to zero. So we have indentation depth, the amount of how deep into the sample the tip actually goes. That's in nanometers. And we do the same for quartz. And if you zoom into this part around indentation depth of 250 nanometers, we see that the load actually becomes negative. That means that we're pulling the tip apart from the surface in order to detach it. So this minima over here and here in the blue curve is basically the adhesion force. We can measure it. It's a small signal, but we can measure it. And as you can see, that happens in an indentation depth that is greater than zero. So the tip is still within the sample. There's still contact between the tip and the sample itself. Through our knowledge of contact area, the real contact area, and the indentation depth, we can get the adhesion force and the contact area at that specific point from the indentation depth. And so I've done this over and over and over again in different combinations from our experimental matrix, and we found. Oh, sorry. It's responding a bit slowly. Oh. Okay. This is the compilation of all test results. We have adhesion force on the y-axis versus contact area at the point of adhesion on the x-axis. And you can see the scales here in squared microns. And we have two groups. We have the red group. That's the chemically inert diamond on silica. And in blue, we have the chemically active silicon silica or silicon quartz and so forth. And we have the different geometries. We have sphere on flat in circles, and triangles are just pyramids on flat. And for different combinations of silica material, and we find that there is a general trends where the adhesion force is loosely related to the contact area for the chemically inert group, with about a power of 0.1. But in general, the quartz or chemically active group shows a scaling of about the adhesion force corresponds to the square root of the contact area, and that implies a physical mechanism. And I'm going to relate this physical mechanism to chemical bonding through two approaches: a fracture mechanics prediction and a bond energy. And the reason I'm going to fracture mechanics first is because through this scaling between adhesion force and the contact area. Basically, the adhesion force, the force necessary to start peeling off the contact from the surface, corresponds to a length scale, to a physical length scale. And that throws us into the realm of cracks. Because if you think about it, when we detach a sphere, when we're talking just about the spheres, because we don't want any plastic deformation, When we try to peel it off, that means that at the edge where the sphere touches the surface, we're detaching them together and we're basically opening a mode one crack. So just from this relationship, we can equate the work of adhesion, the work of the friction of the adhesion force, as the energy required to extend the crack, or the critical energy release rate. That's G sub C. From fracture mechanics for mode one cracks, G sub C is dependent on the critical stress intensity factor, or K1C squared, over the elastic modulus. When we combine them together, I have an expression for K1C, or the fracture toughness, equals the square root of the work of adhesion times the reduced elastic modulus. So going to contact mechanics, you can use the Johnson-Kendall-Roberts model for a sphere on flat surface and find that the work of adhesion, or the adhesion force, is basically this simple relationship between the adhesion force and the radius of the sphere. When we're talking about sphere on a flat. So I can calculate from my data W, put it into this equation, and get an estimate of the fracture toughness from my experiments. And I get fracture toughness of about 0.72 MPAs times square meters, the square root of meter. And compared to that to the reported range for quartz, so basically opening a mode one crack in quartz, so we have to rupture silicon-oxygen bonds. We are well within that range. So that looks promising. And we'll go on to the second calculation, where it's just a simple thermodynamic estimation, where we just estimate the work required to break all bonds in a unit area in silicon-oxygen bodies. In this simple model, the work required to break all the bonds is W. Rho is the bond density, which is known for silica from chemistry as about 4.9 times 10 to the 18 bonds per square meter. Delta G is the change in Gibbs free energy required that's associated with rupturing silicon-oxygen bonds or forming silicon-oxygen bonds. So that is also known from chemistry. And because that's for per mole, we have to divide by Avogadro's number. So this calculation is assuming that all bonding sites are used. We find that the work of adhesion, just from this calculation from chemistry, is more than 1 joules per meter over here. This is the theoretical prediction. And the work of adhesion that we got from we calculated from the data itself, from the quartz data, actually corresponds to a very similar quantity. See, this is the data itself, the work of adhesion from the data, and this is the theoretical prediction, and this is the work of adhesion in a logarithm scale. If we do the same model only just to see what's the work of adhesion for breaking hydrogen bonds or capillary bridges or van der Waals forces interactions, then we see a much lower work of adhesion, about an order of magnitude and a half below our prediction. So this calculation also corroborates what we found from the fracture mechanics approach, where the work of where the quartz core, when we peel off the adhesion, the quartz contacts from each other, it's associated with breaking siloxane bonds. So I'll finish up just with summarizing what I've talked about and why that's important. I showed you that contact area alone cannot explain frictional aging. We need both contact area and the chemical bonding mechanism itself. If you have contact area, but it's not used for anything, it's kind of like having a gun with no bullets. It's just useless. So they work together. We need both of them together to affect the friction. So the chemical bonds are the essential ingredients. I hope I convinced you from my adhesion tests that they are relevant for scales or contacts, which are relevant to small scale roughness in natural faults. So that's the nanoindenture contacts. And also, I showed that, and from that, I hope that you were convinced that the molecular interactions are important for these small scale roughness contacts, which means they play an important role also in fault mechanics. Because if you think about it, faults are fractal, geometrically fractal features, which means that the big bumps that we can say we can see on the map scale are made up of smaller bumps, and those are made up of smaller bumps and smaller until we get to the small scales, which are everywhere, and those are definitely affected by the silicon-oxygen bonding that we see in these experiments. There's still a ways to go, but that's a door that we just opened. And that means that we may need to revise the current frictional models to include these measurable physics and chemistry into them. Because when we introduce these chemical effects, that means that we have a sensitivity to the environments. And that means we can tune our friction models to be more precise and scalable to different geological environments. And that has implications for geoengineering and fault mechanics themselves and earthquake physics when we try to estimate risks and geo risks and associated with the different geohazards, thinking about submarine landslides, which are frictional processes but happening in an aqueous environment with a multitude of chemical species there, for instance. But also for geoengineering purposes, if you think about induced seismicity into old oil formations, like in Oklahoma, they inject water into the old rock formations and they nucleate earthquakes just because they increase pore pressure. If we can manipulate the aging, the frictional aging, the frictional healing just by understanding the chemistry, we might be able to mitigate the size of the earthquakes and contradict the healing that occurs in these faults. So that's like very long-term view, but if we understand the physics and the chemistry, we can use that to mitigate risk and get a better understanding of how the Earth works, and hopefully affect people's lives everywhere. So with that, I thank you for listening, and I'd be happy to answer any questions.
Thank you very much, Nir. It was definitely enlightening for us to hear you. And I open the podium for questions from the audience. Feel free to jump since I don't see all of you together.
Hi, Nir. Hi, Nicholas.
Yeah.
I have a couple of questions. First of all, when you compare diamond and silica adhesion, so is it really correct? Because in general, diamond is geochemically not active rather than a silica quartz. So, and the difference in how we call this hardness, or almost in 10 times, like not 10, but hardness of, yes, we call this hardness. Like diamond is higher than, significant higher than quartz. So maybe I was thinking about Corunt or something like this, like not just diamond, but maybe different minerals. And second, my question, and second question, in real nature, yes, life in fault, we have not just the quartz, but also different minerals, mica, and also fluids. And fluids, for example, they help to heal these faults. Or so in lab, how you account this, or can you comment, please?
Okay, thank you for your questions. Very good questions. I'll address the first one first. Yes, diamond is much harder, much harder than quartz and or any other materials. And first of all, you can see just from these two curves, it's also much stiffer. I mean, that's why we use the hard diamond because it's just we can just use the same tip over and over again, and it becomes dull over time when we change tips, but it's very sturdy. You can see also that the contact pressure is much higher because the diamond is stiffer. But even if the contact pressure is higher, it's much higher, about an order of magnitude higher than the quartz here in this example. Even if we have pressure-induced bonding between diamond and quartz, it would still be that kind of pressure-induced bonding would be much higher for diamond quartz than in quartz because we have much higher contact pressures. And there's a good, and as you see also that adhesion force for diamond quartz or diamond silica is non-zero, right? It also increases as we increase contact area. So that's a good point. It's non-zero because we have other phenomena or other processes that go, whether it's van der Waals interactions. I mean, the diamond itself is oxidized, right? It sits in the air. There's a little bit of an oxidation layer there. Maybe some contamination. I try to clean up as well as I can. But what I'm saying is that, yes, it's non-zero. And there's also the effects of plasticity. I mean, this is energy that I'm doing all the calculation with energy. So some of the energy goes into into plastically deforming the material itself. So all of these things go into the diamond on quartz or diamond on silicon. That means that it's non-zero adhesion. It's a valid point. But even though we have all these effects, we're still just here. This is this calculation for van der Waals. We're still here's the work of adhesion for van der Waals. That cannot explain the adhesion or the work of adhesion that we get from quartz. So yes, it is folded in there because there's always complexity, even in this very simplistic experimental approach. But even though we have this complexity, the overall chemical mechanism of bonding through silicon oxygen is still prevalent. At least that's what I understand from the data. And the second question is that you talked about, your note was talking about water and these types of things. So water, especially when we talk about adhesion and friction at small scales, it's kind of like a double-edged sword. Some water is good because it would promote plastic deformation and
it depends on mineralization.
Also, there's a lot of things going on. That's why I did not start talking about water or change water because it's difficult, and we're taking it step by step. But yes, that's the next step. Changing the humidity, looking at water, different chemistries would definitely have an effect. What that effect might be, it's unclear. If you typically from atomic force microscopy, if they have a little bit of water that enhances frictional aging and actually promotes more bonding because we also have hydrogen bonds, right? But if we have too much water, when we have absorbed layers or like waters that basically takes up available real estate to form silicon oxygen bonds, and we have more hydrogen bonds, which means an overall weaker contact. So it's a thing that people in tribology, in I guess small scale rock mechanics are interested in, are aware of. But yes, it definitely makes the whole story difficult, and it's not as simplistic as I've shown here. I just
Mhm.
want to show you that in a simple, basic way, silicon oxygen bonds are important. But yes, of course, there's more research needed to be done.
Yes, thank you. It was really interesting and
Yeah.
new for me. Thank
Thank,
you.
thank you for your questions. Thank you.
Thank you very much. More questions? Well, I know that also the students are in a rush for the next lesson. So, Nir, again, thank you very much. It was really, really, really enlightening.
Okay, thank you so much. And have a great week.
Thank you, and have a
Thank
good
you.
day.
Okay, thank
Have
you
a
all for
good day
listening.
continuation in Germany.
Oh
Okay.
yes. Oh yeah. I'm back soon home soon.
Okay.
Bye bye. Thank
Bye.
you.
Thank you.
Bye. Bye.